if you think about the momentum unit, one of the things that we focused heavily on was collisions. We dealt with objects colliding with one another, and we saw that the momentum of a multiple object system would be conserved in a collision. We're going to find the same thing happening here with angular momentum. So if I simply do a problem here where I have a disk here, and let's say that this disk has a moment of inertia of I1 and it's rotating, and then I have a disk up here, I2, right? And let's call this omega 1. It's rotating at a certain speed. Well, you know, this is kind of analogous to the object that's moving that we would just drop something on and get it to slow down. If you drop something onto a spinning object, it's not going to spin as fast anymore. So what's going to happen is that I2 and I1 will now be rotating together with a new value, omega 2. So what we can arrive at here is that, well, we're not going to have any external influences in this type of interaction. These two things are going to exert internal forces on each other. They're actually going to exert internal torques on each other, because this one is going to cause this thing to rotate that way. This one is going to cause it to slow down by the action-reaction pair, causing it to have a little bit of deceleration in this direction, which is going to decrease omega 2. Modeling this is very simple if you think back to momentum. So if we take a look here, we've just got to sit there and go, well, this would be L1I, this would be L2I, their initial angular momentums, and then it would be L1F and L2F. The sum of these is going to have to equal the sum of these. L1I, L2I, that's the angular momentum of our system. L1F, L2F, that's the angular momentum of our system there. Now, looking at that, what's going to end up happening is that this thing has angular momentum. This thing is at rest. Let's just say omega 0 here. So we would have I1, omega 1, and then this would just be 0. And then you can actually combine moments of inertia. This is kind of like the analog to the perfectly inelastic collision, because the objects are sticking together. You could write this as I1 omega 2, I2 omega 2, because they're going to have the same rotational speed in the end. And or you could combine the moment of inertias if you want to. And what you have to see right away is that omega 2 is going to be less than omega 1. And the other thing is that we're going to lose kinetic energy in this interaction here. So why don't we say, just for the sake of working with some numbers, let's say I1 is 2 and I2 is 0.5. Right? And let's just say that omega 1 is, let's say it's going 1 rotation per second, so it's 6.28 radians per second. If we want to solve for omega 2, pretty easy thing to do here, because it'd be 2 times 6.28. And then we would have a combined moment of inertia of 2.5, and this would be omega 2. So 2 times 6.28 divided by 2.5 would give us our answer, which works out to be something slower, 5.02. And that is just radians per second. Now let's look at the rotational kinetic energy. We'll look at the rotational kinetic energy of this object initially, and then these two objects afterwards. So you got 1/2 times I, which is 2, times omega squared, which is 6.28. 1/2 times 2 times 6.28 squared, we get 39.4 joules. After that, we'll do the final kinetic energy, which you could combine both of them. You can do them individually. It's up to you. It'd be 1/2 times combined 2.5. 5.02 is the angular velocity. Square it. So 1/2 times 2.5 times 5.02. And we get 31.5 joules. So we have lost kinetic energy in this particular interaction.